over the past 5-6 years, starting with my postdoc at MPA in collaboration with Rashid Sonyaev and also Josalberto Rubino Martin, and now at CETA I've been continuing this work with Dick Bond and other postdoc fellows there. So I'm going to talk, my talk will be having two parts. One, which is going to be about the cosmic microwave background anisotropies, which are the signals you can see, in this red small fluctuations in the background. And then there's also the signals coming directly from the recombination radiation, which is released during this epoch. And I'm going to try to convince you that there's actually interesting things one could learn by looking at this radiation. So first, I wanted to remind everybody, this is a sketch of the ionization history, free electron number density versus hydrogen number density of nuclei of hydrogen as a function of redshift. And at high redshifts, everything is completely ionized. The medium is hot and dense, and we all understand this. So as the universe expands and cools down, you go through several stages of recombination, starting with the recombination of double ionized helium at redshift 6000, and then you go through single ionized helium, neutral helium recombination at 2000, and you end with the recombination of hydrogen at redshift of 1000, leaving a very small residual ionization fraction. And then when the reionization process is happening, everything gets reionized. So when I'm talking about recombination, I'm talking about the high redshift universe, redshift 1000 and above. And in fact, as Avi was also already saying, at low redshifts, there's a lot of messy things happening, astrophysics. And in the high redshift universe, you're very lucky. You can actually do real physics in this environment, because everything is very simple. It's just a hydrogen-helium plasma, no perturbations practically. You have expanding medium, and you can really do detailed atomic physics there. So this picture we have seen already as well, and I don't think I have to convince very much everybody about the fact that we have learned really a lot of things about cosmology just by looking at these fluctuations of the temperature in this in the temperature of the CMB. Just very briefly, of course, here there's the power spectrum of CMB, temperature, and then here a list of cosmological parameters, which already now have really very, very small error bars. So we are in the era of precision cosmology, and we are even being able to talk about helium constraints on helium, existence of helium at redshift 1000, just from the CMB alone, which tells you that because the helium is actually not affecting the CMB power spectra and the fluctuations in the temperature so much that the data is already becoming very, very good. And with recent updates or improvements in connection with ACT, you can rule out that there's no helium at a level of 6 sigma already. And then here's as well the small scale power spectra from the ACT team. And recently the detection of the lensing, CMB lensing. Here's just to show you, this is very high resolution map from the ACT collaboration. You can see all this kind of small structure, and then here's the Sonyaev-Selvich cluster, and people are talking about this a lot. And of course, we are all looking forward to having the real map from Planck. This is the map which they have been releasing last year in July. And you can see, everything is very strongly dominated by signal coming from our galaxy and the interstellar medium, and not by by the signal coming from the primordial CMB. And here just to mention, there's the Sonyaev-Selvich clusters, and there has been a lot of publications, but no real publications yet on the cosmological signal. But what is the important question I'm addressing? Where does the electron fraction come into all this, exciting results from the CMB measurements? So this is the signal we're looking at, the anisotropies, and it's actually produced in the last scattering surface, where the recombination of hydrogen is ending. And Avi was explaining already that when the electrons are disappearing, the baryons and the photons decouple, and you can start to see the acoustic oscillations, the leftovers of these the photons climbing out of the fluctuations in the matter distribution. So and the electron fraction is, of course, describing exactly how this process of decoupling is happening. So if you want to understand cosmological parameters with high precision, precision which is reaching 0.1% and below 1% in particular, then you also have to understand this function, especially around redshift 1100. You have to understand the free electron fraction as well with a very high precision, because otherwise you change the position and the width of the visibility function, and that changes consequently changes your anisotropies. And in particular, if you're asking questions about inflation, the spectral index of scalar perturbations, and also possible running of the spectral index, then you actually are, you really need to know how this is working, and I will show this in what follows in more detail. I'd like to quote this, give this quote from Douglas Scott. If you want to understand 10 to the 16 GeV physics, inflation, early universe physics, you really have to understand the EV physics, the atomic physics, first. So how does cosmological recombination work? Well, first I wanted to remind everybody about the physical conditions during this epoch. So we are in a bath of photons which have a temperature of 3000 Kelvin at redshift 1100 roughly. Then the density of baryons is a few hundred particles per cubic centimeter. In particular, the huge number of photons compared to baryons makes processes, atomic processes, really strongly dominated by radiative processes. So you basically get excitations of electrons by just this bombardment of photons from the CMB. There's so many CMB photons, 10 to the 9 times more CMB photons than baryons. And also things like stimulated recombination and stimulated transitions in the highly excited states because of the presence of CMB photons is extremely important. And then also Avi was mentioning the temperature of the photons and the matter is actually basically equal because of this, until very low redshifts, because of this heavy bombardment by photons. And I didn't mention this, but I will come back to this. Collisional processes for the aspects of recombination are actually not very dominant processes. So if you think about recombination in the simplest way, you just go back to the Saha equilibrium recombination, and you will, predict a recombination history which looks like this. The electrons are just disappearing, and no residual electrons left over even. However, this is of course not what really is happening. Because recombination is delayed strongly, there's bottlenecks, which I will be talking about, which are not allowing electrons to just settle into the ground state by equilibrium processes, but there's a non-equilibrium aspect to the recombination process. And the real history looks more like this. In particular, there's this freeze-out as well, just because the number of electrons and protons becomes so small in the expanding universe that they don't find any colliding particles anymore to recombine. So if you think about recombination in a very simple way, 3-level atom, a ground state, to S state, to P state, and then you continuum, the first thing you can come up with is just a direct recombination to the ground state. That's not working because the photon which is emitted is just immediately ionizing a neighboring atom, and this channel is very, very strongly suppressed. You can completely neglect it. If you include it, it changes the recombination process at the level of 10 to minus 6 relative change. The next channel you can think of is just the recombination to the 2p state, and then a transition to the ground state, Lyman alpha transition. And we all know that the Lyman alpha transition is a very effective line. You have 10 to the 8 transitions per second. However, here again the problem is the photon which is emitted, it's actually stuck in the line. It will scatter many, many times and just re-excite atoms. And because there are so many CMB photons in the Balmer continuum, that's basically equivalent to ionizing the atom. So you cannot go very fast in this channel, and the effective rate at which you're able to go down, which is roughly given by the Sobolev approximation in the expanding medium, is actually of the order of 10 per second rather than 10 to the 8. So suppression by 7 orders of magnitude. That makes another channel very important, which is the 2s1s2 photon transition. So there's no dipole transition here. There's 2 photons emitted in this one transition, and this channel has an efficiency of 8 per second, but I told you this is of the order of 10 per second. So because of this low probability process, you're actually directly escaping, and this channel is 100% contributing basically to the recombination. And if you make the numbers, you find that 60% of all electrons and hydrogen actually went to the ground state in this second order perturbation theory process. So this is buying you a precision in your recombination calculation of order 10 to 20%. And this was already understood in the late 60s by people like this, so Yakov Seldovich and Vladimir Kurt and Rashid Sunyaev, and then also that's the group in Moscow, and then where the initial ideas were found, and then Jim Peebles was also able to confirm these calculations. If you do more high precision if you want to get higher precision, then the first thing you can think of is that, well, let's add additional levels to the hydrogen atom, because of course the effective recombination rate will be there will be some capture into the highly excited states. The effective cross section of the atom becomes, the more states you take into account, it increases. So you just add highly excited states, and you also do helium recombination in more detail, because of course at that time, the early time, nobody was interested in the helium contribution. But if you want to be, have high precision, then you need to include helium. And then at low redshifts, you can also do some more detailed calculations of the chemistry, and that gives you these curves, where you can see, as you increase the number of shells, you're increasing the effective recombination rate, in particular at low redshifts, because at low redshifts is where the bottleneck of capturing electrons is happening. At high redshifts, you have sufficient amount of electrons entering the atom that the blocking is mainly due to the blocking in the Lyman alpha resonance rather than the capture rate. Whereas low redshifts, you actually have the capture rate being dominating the bottleneck. And these calculations were the basis for the widely used RecFast code, which is the standard code which is used in all the CMB analysis so far. And that buys you, as I will show you, a precision of 1 to 3%, which is close but not quite yet where we want to be. So if you want to do the physics for Planck, prepare for Planck, you want to get the 0.1 precision at redshift 1100, because Planck will be sensitive to this level at high L's in terms of the CMB power spectrum. And the list of processes is long, and first thing to say, it's all standard physics. It's nothing, there's no big invention here. It's just radiative transfer, it's atomic physics, and all that you do is you don't make the approximations where you normally say, factor of 2 doesn't matter. You really try to do all the bookkeeping properly. And then the second thing, which is important to say, this is the effort of many people. So the group around Chris Hirata and Yassin Ali Hamoud and also Dan Grin have been contributing very significantly to this. And then also the groups in Russia, Viktor Dubrovich and Gradshov, and also Eugene Khulupenko. I wanted to give a few small, short examples to illustrate some of the physics. So here's I mentioned the 2s 1s2 photon channel is very important. So if you're thinking about the 2s decay in vacuum, then you have an emission profile which looks like this. This is just basically the frequency distribution of photons, the relative frequency to the Lyman alpha. So this is a photon at Lyman alpha resonance, and that would be a photon at very low frequencies. And because there's two photons and energy conservation, it tells you that if there's a photon emitted here, the other photon has to be emitted here. And similarly, if one is here, then the other is also there, close to this. So energy conservation immediately tells you where the other photon is. So let's talk about a photon which is emitted at the Lyman alpha resonance. That means that the other photon is emitted at very low frequencies. But there's a huge burst of CMB photons there. So you actually have the stimulated emission being contributing here. That means that the total process is enhanced by a few percent. Because if you look at the total integral, you just see that the number is slightly larger. That's one thing. Then the other very important, very interesting and insightful thing is connected with the helium recombination. So this is the ionization history again, but here at high redshifts, this is the helium recombination in more detail. And you can see that in comparison to the RecFast calculation, the recombination of helium has been sped up quite a bit. It actually really ends before the beginning of hydrogen recombination, whereas in the earlier calculations it was really going into it. But the main process which is dominant or very important here is the fact that even at this high redshifts, at redshifts 2000, there's already a tiny fraction of hydrogen, neutral hydrogen, 10 to minus 6 or so. But this has enough, contributes enough optical depth in the Lyman continuum that you can actually get rid of the helium photons in the resonances and therefore, accelerate helium recombination because you're wiping out these photons and allowing the electrons to settle in the ground state. And this idea was actually originally proposed, as I understand, by Peebles already. This is written in a paper of Wayne Hu, where he's actually discussing, that uncertainty in the recombination process is one of the things which is important for the future CMB anisotropies. And then the first people who worked this out were Eugen Krolopenko and also Chris Hirata. And this is the figure which we were obtaining shortly afterwards. So in terms of hydrogen recombination, I couldn't resist showing this movie. This is showing the spectral distortion to the CMB as a function of frequency, again, relative to the Lyman alpha frequency. And so the Lyman alpha resonance is sitting here, then the Lyman beta, gamma, delta, and so on. And this is, as a function of redshift, it's just going through the history of recombination. So you get the emission of photons. This is now close to recombination. And then the decrease of photon emission because of the fact that electrons have disappeared. There's no emission anymore. And then you can see as well, the redshifting lets all the photons drift to low frequencies. That's just bringing photons out of the line. And in this calculation, we have included all important processes, photon diffusion in the line. Electron scattering is not very dominant, but we have included it here. Then two photon processes coming from highly excited states, and corrections, quantum corrections due to Raman scatterings. All these kind of things are included, and you can see that photons emitted from Lyman beta, they're eventually drifting into the Lyman alpha line, being re-exciting the atom and so on. All these kind of things are included. If you put all this together, then you get CosmoRec, which is the recombination code which we have been putting out. And here's just a list of things which this code is able to do. It should solve, eventually should be basically representing the recombination process accurate enough to be used in the analysis of Planck data. And the important thing is that instead of running recombination calculations in 6 days on one processor, it takes a few seconds now to run one calculation. So you can really do Monte Carlo with this, and don't have to go back to some approximate representation of the recombination process. And in particular, this is a very easily extendable code as well. You can add dark matter annihilation that's already in. Variation of fundamental constants will be updated soon. And decaying particles is also no big problem. In particular, there's also additional updates which we're now adding, but this code is already available here. So if you show the whole recombination the corrections to the recombination history. This is with respect to the initial recfast, I should say. So recfast as it was 2000. And you can see that this is the relative difference in percent as a function of redshift. At high redshifts, everything is very close to recfast. That's fine. Then you have the acceleration of helium recombination by quite a bit. But this is very early in comparison to the last scattering surface. So the effect of this correction is not that dramatic. And then you have all these changes in the hydrogen recombination dynamics, which are coming mainly from radiative transfer in the lines of in the Lyman series, and in particular in the Lyman alpha line, including as well to photon decays in the 2s continuum and Raman processes. And then here at low redshifts, you have a slight deceleration of recombination because of the fact that the highly excited states are not in full statistical equilibrium, and you're actually not as efficiently capturing electrons. If you convert this into changes in the CMB power spectra, here as a function of L, you see that the temperature power spectrum, you have a 4% change at high L, and similarly for the polarization power spectra. And the important thing is, when you're looking at the NS, you are actually looking at how is the power spectrum tilted from low L to high L, and you see that this is the main signal change here is a tilt in the L space. So that is equivalent to being, it's clear already that this should be messing around in the standard 6-parameter case, should be messing around with NS. And then also baryons are affected, as I will show in a second. There's this wiggly part, which is coming from the fact that the positions of the peaks are changing, and that's changes in the maximum of the visibility function. Here is a more concise prediction for the Planck case, for the 140 gigahertz channel for the 6-parameter case, and you can see we used CosmoRec, so the calculation which should be most accurate in terms of predicting the mock data, and then we run Monte Carlos with Cosmo MC, and we compared the results we obtain if you use the recfast calculation, the initial recfast calculation, and then also the updated versions, Cosmorec. And you can see that in particular NS is biased by 3.2 sigma and 2 sigma for barons. So this is pretty important if you want to really get distinguish between different inflationary models. If you do more extended models, in particular, interest has been in detecting helium with recombination with CMB anisotropies. Then you see that if you add helium and neutrinos, most of the correction is actually now ending up in helium itself. This is a 4 sigma bias, whereas the bias in NS is now having the opposite direction. It's positively biased, but it's only 1 sigma. And baryons is still 2 sigma, actually. So you see that the answer of how these recombination corrections are affecting the whole thing are depending strongly on what kind of question you're asking as well. This was also, I should mention, this was not for Planck, but for a cosmic variance limited case, up to L of 2000, which is not quite Planck plus act pole or so, but close to. Okay, so is the problem solved in connection with Planck and future CMB experiments? The answer is probably it's very close to being solved. So there's the other code which Chris Hirata and Yassin Ali Hamoud were putting out. And, Yassin was the one writing the code. This code is the other code which we are now comparing to, where I'm already discussing with Yassin for quite a time now. We still have some small differences. In particular, here there's differences during helium recombination. That's because my helium recombination model is actually slightly better, but these corrections, 0.3%, are not mattering that much. However, here during hydrogen recombination, we still see some 0.1. That's just out of the box, as the codes are. Compare them, and you see there's a 0.1, 0.2% difference. Here it's only 0.1. We have been tuning around with physics and have been trying to figure out what's going on, and our difference seems to be at the moment, unfortunately, slightly increasing. So we're talking about 0.1 to 0.2% difference at the moment, and Yassin and we are going to meet soon and hopefully get this correction sorted out. But I would say that this is not going to change the kind of expected biases which we have been already calculating that much. It will be probably at the level of 0.5 sigma, maybe 0.3, 0.5 sigma, somewhere there. So not that dramatic, but we want to get it right. And in particular here, one should also mention that there is possibility for additional processes which will, do something. So collisions, for example, I will mention this in the following slides, and then also quadrupole lines. The highly excited states have all these quadrupole lines, which are connecting the levels and could be leading to a redistribution of electrons. And last night, when I was not able to sleep after the jet lag, I was actually writing down I basically coded down the quadrupole lines now as well, so I will have that included soon. There's also interesting aspects, just because the quadrupole lines from the D states, they're actually sitting on top of the Lyman series, so they are actually getting into full equilibrium with the Lyman series lines, and because of the interaction with these photons, so there's interesting radiative transfer as well. So collisions, I told you that collisions, the most important collisions are going to be those which are changing the distribution among the highly excited states in one given n state, meaning the L states are mixed, and these collisions are actually the important thing is that electrons, when they are captured, because of the Gaun factor for the recombination rates, electrons are entering the atom actually more in the low L states rather than the high L states. So redistribution of electrons from there to there is happening mainly due to intermediate radiative transitions. But if collisions are able to transport electrons effectively into the highly excited states, then you're effectively making the hydrogen atom have a larger effective cross-section. So you accelerate recombination. And I told you that at low redshifts, the effective recombination cross-section is important. It can change the recombination physics here, because the more you have available in terms of total electrons which you capture, the faster you recombine. And if you just take collisional rates, which are given by people in stellar atmospheres and so on, then you find that depending on how many shells you include and trusting the rates which you have, that you are expecting something like 0.1% correction there. However, these rates could be off by a factor of 2 or a few, at least in the L states. And I, in particular, wanted to say these, put out these calculations because we're going to hear about collisions later as well in the afternoon session from Hussein. And yeah, so there is uncertainty here. However, I suspect that the uncertainty is not going to change the recombination process at a level which will be very significant for Planck. However, I will come back to collisions in the second part of my talk. And then also, I mentioned already that we are now doing helium. No, I didn't mention it. Maybe I did. Anyway, helium recombination we're doing as well, radiative transfer now. This is all helium lines up to the 10th shell. This is actually something like 27 lines, if I remember correctly, because there's all these triples of lines coming from the triplet singlet transition, which is having low probability. That's the first line in this triple. And then there's the quadruple line from the singlet D to the ground state and the singlet P series. And all these lines are interacting in the same way as hydrogen. You have the redshifting, but then there's also this interesting thing happening at the end of recombination of helium. You get all the electrons, the photons being completely absorbed, because hydrogen is able to just go. Oops. Yeah, maybe I'm not. Oh. Because hydrogen is able to just absorb these photons, and you actually are stopping the feedback process of the higher series to the lower series. These are the kind of things you have to consider. And also electron scattering is very interesting because there's 10 times more electrons than helium nuclei, and you have to do the electron scattering calculation. You can't do it with the normal Fokker-Planck diffusive approximation because the lines are so narrow close to the resonance that you actually have to take into account the kernel, the real scattering kernel, and we have now included that as well. Okay, so my first part, in principle, ends here. I think I've shown the biases which you expect in the 6-parameter case for Planck. I didn't mention the ones for cosmic variance limited case, but the absolute error the absolute bias didn't change, but the relative. So in terms of sigma, it has increased if you go to cosmic variance limited case. And I think it is, it's close to being, at least from the standard physics point of view, from the things which we could think about, we are going to have agreement probably very soon. And the final comparison is done, but it will be very interesting to check for the collisional processes. So I'm very excited to hear that there's new rates now, and I will be very happy to include this. And then there's one thing which I didn't have time to talk about. Mazia Farhang and Dick Bond and we are working on this. Of course, we have been, all this is assuming that there's nothing non-standard happening. You can imagine non-standard things like dark matter annihilation or variation of fundamental constants or decaying particles. All these things you can again work it in. However, maybe there's something in addition. The electron fraction is something which you're just putting into the calculation. So in reality, from the scientific point of view, you should be going somehow, trying to check how is electron recombination, how is the recombination happening? And for that, we were just asking the question how the data alone basically will be able to constrain perturbations in the recombination process. The answer is there is some possibility to constrain it, but the level at which you are constraining is probably not sufficient to really rule out at the level of sensitivity what the dynamics is exactly looking like. So that is calling for something in addition, and I'm going to talk about this in the second part of my talk. Maybe if there are some questions here, we can just have a few. Otherwise, I just continue with the second part. Yes. Mm-hmm.
How much of the change you get in homogeneity, which on small scales can be 10
10 to minus 3, yes. But so the most important aspect is the flows of the matter, but the perturbations in the flow. If you have, because everything is very local, scattering is happening very local, so you're not having a gradient across the flow on the scales on which scattering is happening. So you're actually a second order perturbation only. So at the level of 10 to minus 5, I would say I would expect something. So if we want to get below 0.1%, we're in trouble. But there's many other things which will break down. Born approximation of the hydrogen atom. You can't ignore that the nucleus is moving. You need relativistic corrections. All these kind of things. I'm not volunteering to. Anyway.
Does this explain the discrepancy in the helium abundance between the H2 region observation
The error bar in the in particular ACT was claiming that helium from CMB alone seems to be biased high, even like as high as 30% in YP, so 0.3. But that bias high is larger by a factor of 2 to 3 than the bias you would expect from the recombination physics. So I'm thinking that probably with the next release of ACT data, the bias from helium recombination might be from the recombination dynamics might be already reaching a point more than 0.5 sigma. So probably close to 1 sigma of the ACT error. I should look at that. I was traveling. Traveling very long, actually. So, okay. If there's no other questions, I would like to use the remaining few minutes to talk about the recombination radiation. So from COBE fibers, we know that there's no spectral distortions at very, very large level distortions in the CMB black body. You have the CMB being represented by a black body with a temperature of 2.725 Kelvin with extremely high precision. The error bars are a small fraction of the line width here. But that doesn't mean, of course, that there are no distortions. However, since COBE fibers, basically nobody was pushing in this direction very strongly, or one should say, of course, there's Arcade, the balloon experiment at low frequencies, but there's no real strong improvements in measurements of the CMB spectrum. So these are the best, still as they are standing 20 years, 15 years ago measurements. So what do you expect from recombination of hydrogen? Well, just from the number of of hydrogen nuclei, and the fact that every hydrogen atom should release something like 13.6 eV in form of photons in some way, you expect that the distortions are very small, 10 to minus 9, 10 to minus 8, relative to the CMB. I will show that that is only for the global energy distribution of the photon spectrum, but at low frequencies you see much larger distortions than at very high frequencies as well. And the important thing is that these photons, they are not thermalized. So you emit these photons and they are bouncing around. They are forgetting about what kind of small patch in the universe they came from. So they lose the information about density perturbations as they travel, but they are not forgetting their energy where they were released. Only redshifting brings them to different energies. And from redshift 1000, they are redshifting by a factor of 1000. So even the photons emitted during helium recombination are having the same story. They are not forgetting where at which frequencies they were emitted. For double ionized helium, that's not 100% true. You have to include electron scattering and get some broadening as well. So this is actually some older calculation already. Now we can go, I think I have the slide added, up to 350 shells for the recombination spectrum. But this is showing the spectral distortion to the CMB as it was observed today as a function of frequency. And you can see here in the bound spectrum, Lyman alpha line, then you have your 2s continuum bump coming in, they have the Balmer, Paschen bracket, and so on lines. And at low frequencies, these lines start overlapping because the duration of recombination is not very has a finite large of the order of 20% duration. Also, you can calculate the bound-free spectra. Here, the Balmer continuum, Paschen bracket, and so on. And here, the overlap is already starting at much higher frequencies, just because the continuum emission is always having a much wider line, just because of the thermal electrons. And you can see that the total spectrum of hydrogen, you have these features. You have the continuum spectrum adding something like 13% in terms of the overall emissivity. So from the observational point of view, of course, an interesting question is to ask how large are these distortions relative to the CMB alone. So here's just the same distortion, but now relative to the CMB. And you see at high frequencies, the distortion is really, it's actually shooting up out of, many orders of magnitudes above the CMB itself. However, this is just the Lyman alpha line, or let's say the Lyman series line. So there's no strong spectral features or so. So if you want to look at that part, you will really fight a lot against, the cosmic infrared background. That will be very hard to do, which is the cosmic infrared background being another 4 orders of magnitude larger. If you go closer to the maximum of the black body, you see there's this variability. the level of the variability is very small. So you could think about just similar because this recombination radiation has a template. You could in principle think about digging out in terms of using this template, just like a gravitational wave detection is done with template fitting. Trying to dig in the dirt with the template. So one could think about this here, but it's probably very, very hard. However, if you go to lower frequencies, you see that the relative distortion increases, and from Kobe-Firas, we have a 10 to minus 5 level. That's the relative distortion which they were looking at. So you see, this is this is 2 orders of magnitudes, 3 orders of magnitudes smaller than the Kobe-Firas. From the observational point of view, a Kobe-Firas type experiment could go 3 orders of magnitude slower, probably. And there was recently the PIXI proposal, which has actually shown that that's what they are dreaming of. The question is the frequency. You would want to look at low frequencies if you want to do an absolute measurement. But if you're also thinking about the fact that there's variability here, you could actually think about the differential experiment. I'm going to talk about this. Free is kicking in at below 100 megahertz, but it is there, yes. And I will also mention collisions in a second. Okay, so here's the calculation with higher number of shells. Just I wanted to say that we were not lazy since then, and we have included more shells, and you can see that the low frequency emission is actually increasing because of the more complete hydrogen atom. And you're capturing electrons into the highly excited states, but then as they go down, they can also add to different lines which are corresponding to effectively lower shells. So the interesting thing, and I was very happy to see the plot of which Avi was showing about the observable universe. The interesting thing is these hydrogen lines, they are actually produced slightly higher redshifts than the last scattering surface. So the signal from the hydrogen recombination lines is coming from redshift 1,400 maximum. That's something like 100,000 years earlier than the anisotropies are sort of becoming visible or sensitive to. And I will talk about the helium as well in a minute. So here's helium. From the rough numbers, you don't expect too much helium contribution, but there's different things which are enhancing the contribution of helium. One interesting thing, which I don't have time to explain in detail, but there's all this reprocessing of helium photons by the doubly ionized helium photons are feeding back on the singly ionized helium, and in fact multiplying the number of photons from helium, and then these photons are reprocessed by hydrogen as well, and again amplifying. So you're getting more helium-related photons than just the total number of helium atoms. And the cool thing is, this is of course, if you would be measuring the helium contribution, you're measuring the pre-stellar, absolutely unreprocessed, pure helium abundance from Big Bang nucleosynthesis, which would be a very cool thing, of course. I'm not saying this is easy, and I will come back to this, but I'm just saying there's this possibility. And if you look at the spectrum, how it changes when you add helium, you can see that there's features which are directly related to helium, and this is not including the reprocessing. There's additional, bumps and wiggles coming up, but they are if you're looking at this is a 55% change. Here it's more of a 10%, 20%-ish change, and if you look at the positions of the peaks, they are shifting, which is a nice thing because it's very, if you look at frequency resolution, it's easier to determine where a particular pattern is moving back and forth. There's interesting things happening here. And to complete this plot, these helium lines, they're coming from even higher redshifts. Redshift 2000 and 6000. This is 18,000 years after the Big Bang. So that's pretty cool. If you think about there's something strange happening here, then of course that's well before helium recombination. I will say something about this because there's actually some effect coming from that, even in the recombination radiation. But if something is happening here or here, you know that you are probing, differences between all these stages. So you might be able to see something interesting happening in this different epochs. And variation of fundamental constants. Everything which is happening here in terms of variation of fundamental constants, for example, will be only, affecting this, but you're not sensitive to these epochs. And also in the CMB anisotropies, you're actually not sensitive to this. So this would open a window which is actually going beyond the redshift 1,100. And the way we are thinking about, and I will not be saying that we have a solution or something, but the way we're thinking about this it's very similar to the CMB anisotropies. You're comparing different temperatures on the sky in different directions. But in the business of the lines, you would want to compare the number of photons, basically the differential spectrum at different frequencies. And in terms of sensitivities, the signals I'm talking about here are very small, 30 nanokelvin or something. But if you look at B mode polarization, then sensitivities which people are talking about, they are at that level. So it's not completely crazy to think about this. It's not something you will do just right now or just tomorrow, but it's something which might become interesting in the future. And the interesting thing is you have this template which you could use. If you really rely on your recombination calculation, you should be able to use that. And the lines are coming from all directions on the sky, and they are practically unpolarized. These are things you could use to distinguish things. And the important thing is, of course, you can do standard cosmology with these lines. You can probe, all the parameters these lines depend on, and in particular, you can look at, check the recombination process. You can really basically measure what is the history of recombination, how that is occurring. And just to prove this, for example, the helium spectrum, if you change the dynamics of helium recombination, you get, different differences in the neutral helium spectrum. That's just one way to show it. If you have the recombination being much faster or if it's more like the recombination is more like the initial calculation of rec fast, then you have only one negative feature here. If it's more like the case, close to the case which we have been calculating, then it's two features. And if it's very fast, it will be three, because of fine structure lines. And of course, collisional processes, if you are having collisions at high redshifts, then that changes the helium radiation very strongly. Could affect the helium radiation strongly. And for hydrogen, we have been doing the calculations already. This is an old plot from a 2007 paper. But we have been showing that, if without collisions, you get the black solid line. And with extremely fast collisions in L, you get the emission being, larger here, and you have also changes in the high frequency lines, just because different channels are activated and electrons are redistributed over different lines. And for the rates which we have been using, the differences to the case without collisions is not so large. But if there's a factor of 2 difference, or even maybe in terms of collisional excitation or ionization, a factor of 10, you could suppress or increase the recombination radiation. So that's pretty nice. But is that really enough? If you think about non-standard things, something which is delaying recombination, it's clear that if you're pumping electrons by some ionizing or exciting photons, if you're delaying recombination, that means as well that you're capturing more electrons. And you're in particular removing electrons from which have been already captured, and then they're able to cycle. So you emit more and more photons. If you do this with the dark matter annihilation case, you see that the recombination radiation from hydrogen is affected quite clearly here. In particular, the low redshift signal. If you think about additional alternative, some injection of energy at very early times, you're understanding that you're not in a CMB black body photon field anymore. And then, for example, if you have a Y-type distortion here from Sunyaselovich effect type distortion, then an atom which is sitting in this radiation field, if its frequency in the Lyman continuum is corresponding to this at some particular redshift, then it feels that there is more photons than there should be in terms of full thermodynamic equilibrium. So it will absorb these photons. And as a consequence of pushing towards thermodynamic equilibrium, it will emit photons at low frequencies. So it will recycle high frequency photons and emit them at low frequencies. That gives you changes in the recombination radiation. This is without distortion. This is with a small distortion, 10 to minus 7. Helium spectrum has changed a bit. 10 to minus 6, well, helium spectrum already has changed quite a bit. Hydrogen starts to change, and that's the limit which is allowed by Kobe-Firas. So there's quite some, even orders of magnitudes more emission coming there. And if you look at the variability, then you see, these are not small changes. I mean, these are significant changes. If you would see such kind of changes, it tells you about, there has been some energy injection at high redshifts without actually measuring directly the high energy injection. I mean, you're not. This, of course, 10 to minus 5 would be something you could detect. But for example, in terms of dark matter annihilation, this is like energy injection, which is directly affecting the baryonic matter and not leading to a spectral distortion in the CMB, which is significant in terms of Y. There will be a 10 to minus 9, 10 to minus 10 Y distortion associated with that. Okay, so I think I went through all the things I wanted to really say. Variation of fundamental constants, I'm working on that right now. I've been discussing this with Chris Hirata for some time, but we were both busy. But there's clear that if you change fundamental constants, you're going to shift around the spectral distortions as well. And I leave you with this picture. You have the signal coming from hydrogen from the last scattering surface at redshift 1100. Then you have the hydrogen recombination lines, slightly earlier. Then you have the helium, doubly ionized and singly ionized helium lines, which are really significantly earlier. And you could imagine that if there's something, unexpected happening here, you're actually really probing these different slices in the universe again. And that would be a nice possibility to look at this high redshift universe, which is clearly not simple, but very interesting to think about. Thank you.